Today, we're going to dive into a story about how one of the most spectacular failures in mathematics actually led to one of its greatest triumphs. It's an amazing tale that starts with a problem nobody could solve and ends with a secret hidden inside a simple circle.
Okay, so it all kicks off with this thing right here. This is Fermat's last theorem. And for centuries, this was the absolute Mount Everest of mathematics. It looks so simple, right? But actually proving it seemed impossible.
So here's the deal. The challenge was to prove that if n is any whole number bigger than 2, you can never, ever find whole numbers for x, y, and z that make this equation work. It just can't be done. Sounds straightforward, but for 350 years, the smartest people on the planet tried and failed.
So, fast forward to the 19th century, and mathematicians have this brilliant new idea. They think, okay, what if we stop trying to solve it head-on? What if we could just break it apart? The plan was to factor the left side of the equation into smaller, hopefully more manageable pieces.
And when they did that, this is what they got. Whoa! Suddenly you've got these strange new symbols, that Greek letter zeta showing up all over the place. This was a whole new ballgame. The problem wasn't just about regular numbers anymore. They literally had to invent a new kind of number to even understand this.
And to figure out what those zetas were, mathematicians had to take this huge leap of faith. They had to step off the familiar number line, the one we all learned in school, and enter a completely new mathematical world. A world built entirely out of the geometry of a perfect circle.
It turns out those zetas represent something called roots of unity. And the idea is actually super elegant. You'll love this. Just picture a circle on a graph. Now imagine slicing it into n equal pieces, like a pizza. The points where your slices hit the edge of the circle, those are the roots of unity. They're a totally new kind of number, defined by shape.
So you take these new circle points, you mix them in with all the numbers we already know and use, and poof, you get a brand new number system. It's called a cyclotomic field, which literally means a circle-dividing field. This was the new arena where they hoped they could finally pin down Fermat's theorem.
And this new approach felt unstoppable. But it all rested on one single, absolutely critical assumption. Think about it like this. The number 12. You can break it down into prime factors, right? It's 2 times 2 times 3. That's it. It's always that. That's called unique factorization. And the hope was, if that same simple rule worked in these new circle fields, the proof was in the bag. But then, they made a discovery that just blew the whole thing apart. You see, with our normal, familiar numbers, factorization is rock solid, it's predictable. But in this strange new world of cyclotomic numbers, that beautiful certainty just vanished. The same number could be broken down into totally different sets of prime factors. The rules were broken.
Can you imagine that brilliant, elegant proof they were so close to finishing, it just collapsed, gone? The one fundamental rule it depended on didn't always work. This was a huge, huge blow. But sometimes the most amazing things come from failure. A mathematician, this guy Ernst Kummer, he invents something incredible out of the wreckage. He creates something called the class number. And what it is a single number that tells you exactly how badly the rule of unique factorization fails in any given circle field. And the magic number here was 1. See, if the class number for a particular field came out to be 1, it meant everything was fine. There was no failure. Unique factorization worked perfectly, and the original proof strategy would have worked like a charm.
But here's what they actually found. For some numbers, like when n is 22, the class number is 1. Awesome, the proof would work. But then you get to n equals 23, and bam, the class number is 3. It fails in 3 different ways. For 29, it's 8. And for 37, it fails in 37 different ways. So the strategy failed, but now they could measure the exact size of the failure. So, okay, the main quest, solving Fermat, it looked like it had hit a brick wall. But this is where the story takes this incredible turn. Because all the tools they built to study this failure, well, they ended up solving a completely different problem, one that was thousands of years old.
That prize? It was the answer to a puzzle that had stumped the ancient Greeks. Which regular shapes, like triangles, squares, pentagons, can you draw perfectly using only a compass and a straight edge? For 2,000 years, nobody had the complete answer.
It was the legendary mathematician Carl Friedrich Gauss who found this unbelievable connection. And it basically works like this. First, you pick your shape, your n-sided polygon. Then you build its special cyclotomic field. Step 3, you calculate a specific property of that field. And then, the final check, is that property a power of 2, like 2, 4, 8, 16? If the answer is yes, then your shape is constructible.
And by using this bizarre link between pure numbers and physical shapes, Gauss did something nobody thought was possible. He proved that a regular 17-sided polygon could be drawn with just a compass and straight edge. That's the first new one discovered in 2,000 years. Just think about that for a second.
So, when you step back and look at this whole story, what's the big takeaway here? What's the real legacy of these circle fields?
Well, it's absolutely massive. I mean, for starters, they were born from the desperate attempt to solve Fermat's last theorem. But the tools that guys like Kummer built, they became the very bedrock of modern algebra. And even though they didn't solve Fermat's theorem completely, they did crack it for a huge number of cases. But maybe most importantly, they showed us this deep, almost magical link between the abstract world of numbers and the visible world of shapes.
And this really nails it. The source material says it perfectly. Their role was crucial. Not just helpful, not just interesting, crucial. The attempt to solve one impossible problem ended up revolutionizing everything around it.
And it kind of leaves you wondering, doesn't it? That whole beautiful discovery came from a failure, from numbers refusing to behave the way everyone expected. It makes you ask, what other profound secrets are still hiding out there waiting to be found, right inside the numbers we use every single day?